everybody. All right, so today I'm going to be talking to y'all about the age and current models of the universe. These are sections 29.1 to 29.2 in the text. All right, so let's start off talking about the motion of the universe. Einstein and other astronomers at the time, so early 1900s, didn't think that the universe was in motion. Einstein was actually very against that idea. So he introduced this thing called the cosmological constant, which is a hypothetical force acting against gravity to keep the universe at equilibrium so that it was static. This was later disproven, and Einstein called it the biggest blunder of his life. So in the 20s and 30s, the theory of the expanding universe became more widely accepted. So in the idea of a finite universe, so imagine the universe as a big ball, due to gravity, our universe needs to be expanding or contracting. So for a contracting universe, gravity is causing all of those other planets and galaxies and stars to collapse in on itself because gravity is a attractive force. It would be pulling everything together. And then for an expanding universe, so the universe as a ball is getting bigger, that means they must be moving very fast away from each other. So imagine just throwing something up in the air. It has to be moving very fast to essentially break away from gravity. And once it's not moving very fast, it will accelerate back down towards Earth. And the reason that scientists knew that there was actually an expansion rather than a contraction was observing a redshift in distant galaxies. So that redshift is essentially the Doppler effect. So here, if this is some distant luminous object, if it's moving away, that light that's being emitted is essentially being stretched out. The wavelength is a little bit longer, more towards the red end of the visible spectrum, rather than on the other side. If something was moving towards you, it would be shifted towards the blue or violet side of the visible spectrum. Okay, so the Big Bang, it's an explosion of the whole concentrated universe at what we'll consider the beginning of time. Hubble time is our predicted age of the universe. So, assuming a universe that's expanding at a constant rate, time can be, this is called Hubble time, can be found by dividing some distance traveled by speed. That speed can be calculated by multiplying the Hubble constant, this h value, which is the current rate of expansion, by a distance. And then kind of substituting one of those formulas into the other one, time of the universe was calculated as 1 divided by the current Hubble constant. So the first estimates of the age of the universe were around 14 to 15 billion years old, depending on the Hubble constant that was calculated. So again, the Hubble constant is the current rate of expansion, and this whole formula assumes a constant rate of expansion. Okay. So a decelerating versus an accelerating universe. Astronomers thought that the universe should be slowing its expansion rather than speeding up. And this is because of gravity. They thought that gravity was essentially slowing that expansion down. So gravity is pulling inward and slowing the expansion of the Earth. So they thought that eventually it would stop and start kind of collapse back in on itself. But to determine that, they needed two things: a bigger telescope and a luminous standard bulb. So a standard bulb is a luminous object at least 1 billion light years away. And they didn't actually have these two things until the 1990s. So 1990s astronomers observed a type 1a or multiple, so supernovae, that are standard bulbs. So that that type of supernova is specifically a white dwarf, accretes material from a nearby star, and then it collapses and explodes. And so they're able to see this really, really bright supernova in comparison to its surroundings. And what they were able to see is that the universe expansion is actually accelerating rather than decelerating. So observing these supernovae, they saw that the supernova were um, dimmer than they expected using the Hubble constant and the rate that we thought the universe was expanding at. So they saw this multiple times where they saw something dimmer than they expected, and they were able to conclude that the universe is accelerating. So those objects were further away than they would have predicted. And so here are some of those images that were taken. On the top, you can see the supernova, and then below is either right before or after the supernova explosion. So, crazy thing. And actually, I think in 2011, the Accelerating Universe researchers got the Nobel Prize because this was a groundbreaking discovery. Big question was, how is this happening? We would expect gravity to be slowing down the expansion rather than something speeding it up. And we call that something dark energy. It's some form of energy acting against gravity, causing that speeding up. What is it? Short answer, we don't know. Potentially, this is kind of a quantum mechanical theory. This like energy in the vacuum of space, this tiny elementary particles flickering in and out of existence. But dark energy has never been detected or measured, so we really don't know what it is, which is pretty exciting. So here is a diagram of, kind of the most modern theory of the expansion of the universe. So we start with the Big Bang, and right at first, gravity, all that matter is so close together that gravity is slowing the expansion of the universe. But then somewhere close to our present time, dark energy has caused an expansion of, or an acceleration of that expansion. So the new age of the universe. So it has been calculated, given that new information about the accelerating universe, that the universe is about 13.8 billion years old, plus or minus only 100 million years. So really, in the scale of everything, that's not a huge percent error, which is pretty incredible. The accelerating universe means that the Hubble constant is actually going to be changing with time, because the Hubble constant is the current rate of expansion, which if we're accelerating means that it wasn't always the same number. Currently, it's about 70 kilometers per second per million parsecs. And using uranium and uranium decay to date distant stars, the oldest known stars are over 12 billion years old, but still within that calculated age of the universe as 13.8 billion years old. Okay, so here's some models of the universe. Actually, not quite yet. This is kind of some base information first. So to create these models of the universe, we first need to base it off the cosmological principle, which means on the large scale, the universe is the same everywhere. So the rate that we observe of expansion in our neck of the woods is the same on the other side of the universe. The fabric of the universe, or space-time, is expanding everywhere all at once. It's not like it originated from some point and rippling outward. It's just all expanding at the same rate everywhere. So this one kind of blew my mind. I thought it was pretty cool. Red shifts that we're observing are due to the stretching of space-time rather than galaxies moving through space. So it's not like a leaf like traveling across a pond. It's more like you're stretching out dough with raisins in it, and those raisins are moving further apart. So the book had this image of, imagine if you drew a wavelength on a balloon, and these are all little galaxies, and then you blew up the balloon. That wavelength itself is going to get stretched out, not because of, this dot is moving somewhere else, but because the fabric between these dots is stretching out. Pretty cool. Great. So further trying to figure out a model for the universe, we need to talk about average density of the universe. So density, as you've calculated before, is mass divided by volume. A low density universe is going to keep expanding. There's not enough mass to have enough gravity to pull it back together. a high-density universe could stop expanding and collapse due to gravity. And then critical density is the perfect density, so the expansion will slow to zero at some point. Whoops. So here are a few different models of the universe. So over here on the left, if you look at this first picture here, this is a recollapsing universe. And this is kind of modeled on this graph over here by the curve number 1. So this says that from the Big Bang, this is a low-density universe. Sorry, switch that. High-density universe, where eventually there's enough mass that gravity will pull the universe back in on itself. And that theory is called the Big Crunch. So eventually our universe will stop expanding, it'll collapse back on itself and crunch back down to as it was at the moment of the Big Bang. And there's actually a theory that there's an oscillating universe where that process of Big Bang and Big Crunch keeps happening over and over again. The second curve here, this is a universe that keeps expanding. These other models are all open universes. This first is a closed. So that's better modeled by this third diagram here. So it's going to keep expanding. This third curve is critical density. And so that's this second diagram here. Eventually, this expansion will slow to a stop and it will not continue expanding. And then the fourth curve is kind of the most widely accepted at this point, and that is where we had the Big Bang. The universe was slowing for a little bit because of gravity, but then dark energy starts to accelerate the universe. All right, so critical density. Using the Hubble constant and the universal gravitational constant, the critical density of the universe has been calculated to be this really, really tiny number, 9.6 times 10 to the negative 27 kilograms per meter cubed. And again, that's the density where eventually the universe would stop expanding. And this is equivalent to 1 grain of rice per 10.5 kilometer cube of space. So imagine if we were to take all of the galaxies and planets and stars, crunch them all up, spread them out over the universe, 1 grain of rice per every 10.5 kilometer cube. So current estimates for the density of the universe. If we include all light and dark matter in the universe, the density of the universe is estimated to be about 30% of that critical density. So it is less than the critical density. So that would give us a low-density universe that keeps expanding. If we include that light and dark matter as well as dark energy, then we have a density of the universe only about 70% of that critical density. So regardless of which of these that we take, evidence points towards the continuing expansion of the universe. So given that information, we can have a couple of different models to choose from when estimating the age of distant galaxies. So depending on the model chosen, the critical density model versus the standard model, and that standard model is, let me go back, given these two calculated densities here, the 30 and 70%. It's there as well, sorry. The age of the distant galaxies depends on which model is chosen. This model on the right is kind of our more standard model at this point. But here's like a small excerpt from a table in the book, and you can see the differences. Given that standard model, we can estimate that, the age of different distant galaxies are a little bit younger, right? No, older, sorry. Okay, I'm gonna stop there. Okay, bye. How do I stop this?